Hello, everyone. My name is Zhongxu Zhai. I'm a postdoc at the University of Waterloo. Today, I will introduce our recent work on the cosmological constraint from small-scale clustering of BOSS galaxies as a part of the Aemulus Project. Let me first briefly introduce the Aemulus Project. It is a collaboration work with many people in different institutes. The main targets of the Aemulus Project is to understand and model the evolution of properties of galaxies and documented halos. The main methodology is based on a suite of high-resolution n-body simulations with different cosmological parameters. And in order to understand the dependence of these statistics on parameters, our main approach is to develop and construct precision emulators. So far we have constructed emulators for halo mass function, halo bias function, and galaxy collision function. And my talk today here will be on the BOSS clustering analysis using clustering emulator. So for this clustering analysis, we focus on the clustering measurement at both linear and non-linear scale. In particular, we have clustering measurements from 0.1 to 60 meg/second. So it is deeply in the 1 halo term. And our main goal is to measure the linear growth rate of structure. And in addition to that, we also introduce an extra parameter, which is called COMF, which is velocity scaling parameter. So we use this parameter to scale the velocity of documented halos from the simulation. And we let this parameter to be a free parameter and determined by the data. So if this model, so this parameter can mimic the effect of modified gravity at the corresponding scales. And the data will tell us if this velocity scaling parameter is consistent with general relativity or it has some deviation. So before I introduce our the application to BOSS galaxies, we first do a pilot study or theoretical study. So in this study, we focus on the CMS galaxy as our target sample at redshift 0.55. We built some emulators based on Gaussian process. And emulators can make predictions for both real and redshift space correlation function. So here the 3 columns shows the WP on the right-hand side, sorry, the left-hand side, the projected correlation function. And then the middle column is the RSD multiple, and the right-hand side is quadruple. So in the top panel, we show the measurements of this clustering from simulations directly as open symbols. And then we use optimized or trained emulators to make predictions. So as you can see here, the solid line from the emulator can match the direct measurement from the simulation very accurately. There are some randomly chosen model from our simulation. And in order to evaluate the overall performance of this emulator, we compare the prediction with hundreds of test models. The overall performance is shown as the shaded area in the bottom panel. As you can see here, from the 1 to 10 meg/second, which is the most informative scale, our emulator has accuracy of better 1%. And in the other scales, the emulator can be comparable or better than the sample variance or the training error. Now with this emulator, we can investigate the question whether there is more constraining power to measure linear growth rate compared with linear scale measurements. So this can be done by running a few recovery tests. Basically, we just randomly pick a few models from our test sample and use the data vector as the observational data. And then we run MCMC-like methods to constrain the cosmological parameters. After marginalize all these galaxy bias parameter or cosmological parameters, we project the constraint on f(8) in the right-hand side. So compared with the linear scale measurements, which is the blue star here, our scale measurements, the small scale measurements is quite accurate. The right-hand side figure shows the dependence of the uncertainty as a function of minimum scale. So the blue star from linear scale measurement has a 10% error. But if we go to small scales until 0.1 meg/second also, it can have a measurement of f(8) roughly 5%. So this is improvement, or it's a factor of 2 improvement compared with linear scale measurements. With this emulator, we can also investigate whether there are more constraining power from quadrupole, or if we have an emulator that can make infinite accurate prediction, what is the uncertainty? So these questions are all answered by these emulator methods. Then we apply this emulator method to the BOSS galaxies. So before we apply the constraints or measurements, we first select the BOSS galaxies. Since BOSS galaxies include both CMAS and low Z, it has a wide redshift range from 0.2 to 0.6. So the first cut is redshift. We split the galaxies into 3 redshift bins, and so we can build emulators for each redshift bin separately. In addition to these redshift cuts, we also have additional cut based on their brightness. So in particular, we rank order the galaxies by their brightness in each thin redshift bin, and then we only choose the first few for the brighter galaxies, the first few bright galaxies, and until the galaxies can reach some predefined number density. So this gives us a sample that the galaxy has a constant number density across redshifts. So in this case, our selection can give us a semi-complete or volume limited sample. So the figure here shows the distribution of brightness for 3 redshift bins, the 3 columns, and also for north and south galactic caps separately, the top row and bottom row. So after this brightness selection, it gives this selection is very close to a hard cutoff at some scale. And then with this resultant galaxy catalog, we measure the clustering, shown as the square and the arrow bars here. With these measurements and the trained emulator, we now run a constraint. Here, I just want to remind the features of our model. The model has a high dimensional parameter space. It has close to 20 free parameters, including cosmological parameters and galaxy bias parameters. For the galaxy bias parameters, we use a halo occupation distribution to connect diagonal halos and galaxies. And in this model, it has basic HOD parameters that can describe the number of centrals and satellites within the halo. We also introduce some additional parameters, such as the velocity bias for both central and satellites. It means that our central or satellite galaxies can have some additional velocity component compared with the diagonal halos. We also introduced the concentration parameter for satellites. So this parameter means the distribution of satellites can be different than the NFW profile. The last piece of information is from assembly bias. From numerical simulations, we know that the clustering of halos and galaxies can have some dependence on properties other than halo mass. It can be halo age or concentration or environment. And in our model, we choose the environment based on the local density of halos as our assembly bias model. So after this, this completes our model for galaxy bias. The solid line in the figure shows the best fit model. As you can see here, our model can make very good fits to the data. With these constraints, we extract measurements of F sigma 8, and we also compare our measurements with some other analysis in literature. Our latest measurement is the blue and black squares for different choices of the velocity scaling parameter, but they give quite consistent results. So the first thing we can see is that if we compare the linear and nonlinear scale measurements, the nonlinear scale measurements is quite accurate. The uncertainty is much smaller than the linear scale measurements. But on the other hand, we find that our measurement has some tension compared with Planck, which is the horizontal black shaded area. So, and this tension can be more significant for the high redshift subsample. At the redshift 0.55, the tension is about 4 sigma. For the other 2 redshift bins, the tension is slightly better. So from these constraints, we can look at individual parameters, and this can tell us the tension more clearly. So for instance, this contour plot shows the constraint on sigma 8 and gamma f, which is the velocity scaling parameter. if we just look at the 1D distribution or the constraint on the individual parameters, it looks like Planck or general relativity can be very well constrained, or it is consistent with our measurement. But given this degeneracy, some parameter combination can be offside. So on the right-hand side, we show the sigma 8 squared times gamma f, which is, we believe, the clustering amplitude from the RSD effect. So the vertical red line corresponds to Planck, and the difference of the offset is very clear in this figure. So then we try to understand where this tension comes from. The direct analysis is to look at the scale dependence. So we can restrict analysis within some particular scale and evaluate their constraints. So in particular here, our fiducial analysis has measurements from 0.1 to 60 meg per second. And then we only restrict analysis above 0.4 meg per second, which is the purple histogram. And also we have additional test that only uses the linear scale measurements above 3.5 meg per second, which is green histogram. So for the first two redshift beams, the low redshift and middle redshift beams, it looks like a linear scale measurement is quite consistent with Planck. It can also increase the F sigma 8 measurement for the high redshift subsample, but it's not as significant as the other two redshifts. It shows that the tension is fully driven by these nonlinear scale measurements. We also see this result from our eBOSS analysis, which is based on paper last year. So this figure shows the measurements, the constraint on emulator and S8. The difference between the left-hand side and right-hand side is that on the left-hand side, we only show the linear scale measurement. On the left-hand side, we show the full scale measurements, the blue and green contours. And on the right-hand side, we only use the linear scale measurements. So this is very similar to our BOSS analysis. The small scale can tighten the constraint, but show some tension with Planck. Then we also compare our measurements with the other clustering analysis using similar methods or similar data. They all seem to show that this amplitude is lower than Planck. And the tension, the difference can be like 10 or 20%. It is consistent with our galaxy lensing analysis, because in this analysis, we know there is lensing is low effect, that the lensing amplitude is lower than Planck by like 30%. So we also compile some measurements based on galaxy lensing in the lower panel, as shown here. It seems to show that the clustering analysis and the lensing analysis based on galaxies have some tension with Planck. So then we can investigate if there is a assembly bias from these small scale clustering measurements. So in our model, the assembly bias is modeled by some 3 parameters depending on the halo environment. We can simply turn off the assembly bias by fixing the assembly bias parameters. And then with this reduced model, we reanalyze the BOSS clustering measurements here. And so with fewer parameters, the constraint is tighter, not surprising, as shown in these contour plots here, the red contours. But on the other hand, these contour plots are quite consistent with the model with assembly bias. So it tells us that the assembly bias won't able to solve the tension of the clustering amplitude. Second, the bias doesn't bias the cosmological constraint. So there are some possibilities for this tension. For instance, there might be modification of general relativity or some massive neutrinos, which is our next simulations in the next couple of months. And we can also there are also some missing baryonic processes, and there are all some works that we have been working on. But in addition to these investigations from the theoretical or modeling side, we can also ask a question that if this result has some dependence on how we select galaxies. Because in our previous analysis, we select galaxies to have some number density, but this number density can be sort of arbitrary. So we can add or remove galaxies such that average brightness of the sample is different. So in this case, we focus on the CMS redshift. and choose a different number density shown as the blue, the figure on the left. And then we build emulators for different number density and redo the constraints. The contour plot on the right hand seems to show that the constraint is kind of stable. No matter how the density is chosen, the constraints are consistent with each other. If we look at the constraint of sigma 8 as shown in this figure, we do see some variation as a function of number density, but they all seem to be different from Planck. So this is just one selection based on luminosity. But for both galaxies, we have some other properties such as galaxy age or color. So we do some further analysis and project measurements of gamma f and sigma 8 on the right-hand side. It seems to show that all these clustering measurements, no matter how we split galaxies based on different galaxy properties, the clustering measurement or the RST measurement is very similar or consistent with our full-scale BOSS clustering measurements. So this is the main results of my talk today. We have some other follow-up work that we are working on. I'm very happy to discuss more about it in the discussion session. So I will stop here and thank you.